Welcome back to Code Meets World, and today we're going to be looking at the next problem in the math and geometry category, which is spiral matrix. So the instructions here are pretty simple. We're going to be given an m by n matrix, so that means it doesn't have to be perfectly square, and we need to return all elements of the matrix in spiral order. And I think we're shown here what spiral order means. So starting with the upper left, going around the perimeter, and then slowly working our way in. And it looks like we need to return a single array that contains these values in the spiral order. So 1, 2, 3, then 6, 9, 8, 7, 4, 5. Yeah, we return it like that. Here's an example on a 3 by 4, 3 rows, 4 columns matrix. So yeah, let's head down to the whiteboard and talk a bit about this. I've drawn just the 3 by 3 that they showed, 1 through 9 in the example. And I'm racking my brain to think of a way that we could do this, which isn't just brute force in parentheses. Because if you watched my last video, which I just linked at the top, there is a matrix problem, but you can do a cool mathematical trick to avoid having to do the brute force solution. So I'm thinking if there's anything like that we can do here, but I really don't think so. I think we have to just go in the spiral order around the matrix and add all those values to an array. So what I mean is, for instance, if we have our answer, we'll call it solution. I think we just start at the top with 1, and we add that. We jump to 2, we add that, then to 3, then to 6, 9, 8, 7, 4, 5, 6, and we add all of those. I'll write them out just so we have it. But actually writing the code to do this might be a little bit tricky, because I guess the hard part about this is automating it so that it works on any sized matrix. And so the way I'm kind of thinking of doing it is writing 4 loops, right? So I think our solution can have 4 loops, maybe a 5th loop to run the 4 loops as many times as we need to. But I'm thinking what we're going to do is first we're going to go to the right as far as we can. Then we're going to go down as far as we can. Then we'll go left as far as we can. I should have drawn this in a different color. So we'll go right as far as we can, down as far as we can, left as far as we can, and then we will go up as far as we can. And once we do that, that's one cycle of the spiraling, so basically one spiral. So then we need to do the same thing again on the inside. So again, we'll start by going to the right as far as we can, and we're done. In this case, we've gone right and there's no other values to process, so we finished. So I think my strategy is going to be just to do these spirals as many times as needed until we consider all values. And the hardest part is definitely going to be figuring out how to make the bounds of the loops work so we continually go in each time. So I'm going to pull up the code and also the whiteboard on the same screen. So while I write the code, we can look at the effect that it's going to have on the spiraling. Okay, so now I'm back at the code and I have the whiteboard at the top of the screen, just showing the problem here, 1 through 9. And I have a little cat that's going to represent where we are in the matrix so that we can keep track of my thought process as I'm writing the code for doing this. I think this will help me a lot and hopefully help explain things visually. So the way I'm thinking of setting this up is, well, first we need to probably define a few things. M is going to be the number of rows. So that's just the length of the matrix. N is the number of columns. So we can say the length of the matrix, and we can pick any row. We'll pick the first row. Good. So then another thing we need is the solution array where we're going to store everything. So I'll call that SOL for solution. We need a starting row and column so we can keep track of where we are. And the row and the column is going to be represented by the cat in my picture. So I'll set those both to 0 at the start. And I'll just put, for kicks, this is the position of the cat. Fix the spelling mistake. And then we need one other thing. So on the whiteboard, I talked about how we need a method to keep track of where we've already been. So the way I'm going to do this is by setting 4 bounds on the matrix. One for the upper, right, lower, and left bound. And the bounds are going to let us know how far we're able to go on one spiral. And then over time, we're going to constrict the bounds in so that the spiral gets smaller and smaller. And I'll show an example of that as I go. But I'm going to label these, I guess, right bound. That's what RB is going to stand for. Right bound, down bound, left bound, and up bound. And we'll set those all equal to 0. Like that. Okay, so now that that's all defined, I'm going to have an initial while loop that says while the length of solution is less than right n times m, we keep going. Basically what I'm saying is after we do a spiral, which again is going right, down, left, up, after we do that and add everything to our solution, if we've added all the values, meaning the length of the solution is the same, has the same number of values as our entire matrix, we know we're done. Because they have the same number of values, we must have considered everything. If they're not the same, that means we need to do another spiral. And that's what this while loop will control. So first thing we want to do is, again, given the pattern, we want to go to the right. So looking at our cat there, we want to go consider the whole top row first, moving to the right. So I'm going to need another while loop. So I will say while. Now here's where we use our bounds. So while column. So this first going to the right means iterating over the columns. Going from 1 to 2 to 3 means going from column 0 to 1 to 2. So while our column is less than the right bound, and this leads me to an error. My right bound isn't 0. My right bound is the number of columns, which is n. My down bound has to be the number of rows, which is m. This makes sense, right? Because for right bound, if we set right bound equal, in this case, to 3, that means after I do 0, 1, 2, for the number of, these are the columns, column 0, column 1, column 2. Once I hit column 3, I can't go there because there's nothing there in the matrix. So that's why I'm setting the right bound to 3. Same with down bound. I'm setting that to 3 because after we consider row 0, 1, and 2, we don't want to consider row 3. So that's the bound. My left bound and upper bound can stay at 0 because when we move left, we're moving back towards column 0, and when we move up, we're moving up towards row 0. That's a bit confusing, but hopefully that makes sense and will make even more sense once you see it in the problem. So while column is less than the right bound, what I want to do is add what we're at to the solution. So solution.append, and this will just be matrix, row, column. And so looking at the cat here, we're starting on 0. So the first thing we do is we're starting on 0, 0. So the first thing we do is we add 1 to our solution, which is what we want. In fact, I'll even write that in so we can see it. So we'd write in the 1 first. And then what we need to do is increase the column. So say column plus equals 1. And what that's going to do is it's going to move the cat over 1 to the next value. And so then we would just loop again. So it would check while column is less than right bound. It's in column 1 now. And remember, right bound is equal to the number of columns, which is 3. 1's less than 3, so we go into the loop. And we append the value. So we append 2. And then we increment the column by 1, which is going to, again, move our position over 1. And then we'll check is 2 less than 3? It is. So again, we add the value. And then we increase the column. So we actually move the cat off the end of the matrix. And now when we go into the while loop, column would equal 3. That's not less than 3. So we break out of the loop. So now we've finished this. So now what do we have to do? Well, we know the cat needs to get to 6 to start the next part of its spiral by going down. So I'm going to put the cat on value 6 by doing this. I will say, I guess, column minus equal 1. So by doing that, it brings the cat back to the 3. And then I'm going to bring it down 1 by saying row plus equals 1. So by increasing the row, I'd be moving the cat down to 6, where it needs to go next. And then I think there's one other thing I need to do. I need to update the bounds. Because I just completed the first row, I never want the next spiral to go back to that top row ever again, because I've already finished it. So right now, the upper bound is set for 0, meaning we can consider row 0. I don't want that. I want to move the upper bound down a row so that we never go above that bound ever again. So to do that, I can take the upper bound and I can add 1 to it because it's currently 0, now it's 1. So now we will never put the cat above into the first row ever again. Okay, so I think that's how we spiral, or that's how we do the first part of the spiral, by moving to the right as far as we can go. Now I'm going to copy this, which is sometimes dangerous, but I think it'll save us some time. The next thing we need to do is move down. We're going to do the same thing, but just change the values a little bit. So to move down, I need to go down rows. When we moved to the right, we were going from column to column. To move down, we're going from row to row. So while row is less than, and now I need to use the down bound because we're going to move down towards the bottom. So while row is less than down bound, we can append whatever we're at. So that will append 6, because that's where the cat is. And then we will increment the rows, which will move the cat down to the 9. And then we need to check the while loop. So the row would currently be on number 2, because we're on row 2. Downbound would be 3, because we set it to the number of rows. So we iterate again, we add the 9, because that's where the cat is. Then we add 1 to the row, so the cat is actually going to go off the end of the matrix by going down another row, which doesn't exist. And now the while loop doesn't fire anymore, and we come outside of it. So just like the last time, I'm going to first position the cat back to where it was. So I'll say row minus equal 1, which will move the cat back to the 9. And then I will take the column and subtract 1. So we move to the 8, which is the next place we need to go in the spiral. Finally, because we just moved down this row, I never want the cat to go to the rightmost column anymore because we already finished it. So this time I need to update the right bound by subtracting 1 from it, because the right bound started is the value n, which is the number of columns, which is 3. So now I'm going to subtract that to be 2. So now the cat cannot move any more right than this middle column. Okay, so I think that's how we do the down. Now let's move on to left. So again, I'm going to copy paste because it's easier. To move to the left, again, I'm doing columns just like I did when I was moving to the right. But this time we need to check if columns is greater than or equal to the left bound, right? Because we're going to be starting here on the 8 and we're going to be moving to the left. And we do that by subtracting columns. So we'll start at the 8, we'll move to the left, and we want to move to the left while columns is greater than or equal to left bound. And remember, left bound is 0. So we're going to move to the left all the way until we get to column 0, and then we'll stop. So the first time this loop iterates, the cat will first add the value the cat is on, which is 8. Then we'll subtract 1 from the column, so the cat will move to 7. Then we will go into the while loop again because we're now on column 0 and that's greater than or equal to the left bound, which is 0. So we'll add the next value, which is 7. We will subtract 1 from the columns, so we moved off the end of the matrix into the negative values, which again is wrong, but we'll correct that by first adding 1 to the column, which brings the cat back to 7. And then we'll subtract 1 from the row, which brings the cat up to 4. And then again, just like we've been doing, because I just moved to the left, that's going to affect the lower bound because we never want to go back into that last row. So I'm going to take the down bound and I'm going to subtract 1 from that because it's currently 3 and I want to move it so that it is, so that the cat never crosses that middle line to go lower anymore. Okay, and just one more, and this one's going to be very similar to down because it's also moving vertically, and that is the up. So for this one, finally, it's going to be the row, and we're going to check just like the last one while we're greater than or equal to the upper bound, because we're going to be moving up until we get to row 0. Or in this case, we've actually updated the upper bound so that we can't actually go up to this top one anymore. So we're not allowed to go any higher than the middle row. But anyway, that's captured by upper bound. And then we want to subtract rows as we go so that the cat moves up the matrix. So what happens here is we check our while loop. The first thing, we fall into our while loop, we add the 4, which is where the cat is. Then we subtract 1 on the rows, so the cat actually moves up to the 1, which we don't want. So after that happens, we want to add 1 back to the rows, so the cat comes down, and then add 1 to the columns, so it moves back over to the 5, which is where it needs to go next. And finally, like we've been doing, because we just moved up, we need to modify the left bound, which is the only one we haven't modified yet. So we don't want to go any further left than that outer row. So we take the left bound, which is set at 0 at the start, and we add 1 to it. Okay, I think we're making a lot of progress here. In fact, after we do all of this, we can return the solution. And part of me is thinking this might be right. I know this has been a long video, so thanks everyone for staying with me. Okay, so we passed the first test case, which is amazing, but something went wrong with the second one. So we were expecting, which is this. So we actually solved the 3x3 one, which is great. But this case 2, we've added the 6 twice because my solution has everything correct, exactly like the expected should, but it adds the 6 again. If I had to guess, that would be because at some point, one of these while loops has finished and we've completed our solution because we did. We had every value correct. But then it kept going to the next loop. And then it somehow, my bounds are messed up and it added another value onto the solution. So this might not be the best way to handle this. But I think what I'm going to do is create a function that just checks after each of the loops if the length of solution is equal to n times n times m, like that, if those are true. And then what I can do is simply say, after we do everything, we can just say if check on the length of solution, if that's true, so if the length is equal to n times m, we can just return the solution like that. And I don't like, this feels a little bit like over-engineered, I guess, to add this at the end of each thing. I guess I don't need it on the last one. But yeah, let's run that and see if that fixes the problem. Okay, it does actually fix the problem. So let's submit and see if this works. Okay, yeah, that worked. Pretty decent. Again, I'm not looking too much at the runtime or memory because sometimes they're not accurate, as we've seen. But this was a tricky one. This ended up being a long video. I hope this made sense. And yeah, let me know in the comments if you have any questions. In the meantime, I might also look to see if there's a better way to do this, because this felt awfully hard-coded and a bit brute force, especially with updating where the cat was, where our pointer was all the time. I don't know if that's the best way to do it, but this is what came to me, and hopefully that makes sense. And yeah, maybe I'll make an extension to this video to talk about another way that this could be done. But thanks so much, and I will see you in the video soon.